Welcome back. In this video, we're going to begin to think about, converting between radians and degrees. So previously we've talked a little bit here about this unit circle, and each of these measurements on the unit circle has both a degree as well as a radian measure. And there are, infinite degrees on this unit circle. It goes around and around and around forever. And there's tons of sub measurements, we should say, in here between these standard units, which we use, which are 30, 45, and 90. So our multiples of 30-degree angles or pi/6 angles, as well as multiples of 45-degree angles. So when we think about converting between degree and radian measure, we want to think, well, what do we know? Just like when we're converting between units, say from feet to miles, we say, well, we know that 1 mile is 5,280 feet. So how many degrees are in a radian, or vice versa? Well, we know one trip all the way around that unit circle. That one trip goes from 0 to 360 degrees, or rather 0 radians to 2 pi radians. And we don't generally need to write that R for radians, it's just understood, but I'm writing it right now. So we know that 360 degrees equals 2 pi radians. Furthermore, we can use that to create a unit fraction. And so a unit fraction is a fraction that's equal to 1. And when you're thinking about canceling, especially maybe in your chemistry or physics class, and you're changing or converting units, you match up unit fractions in order to convert. So I can say here that 360 degrees over 2 pi radians, since that is the same quantity divided by itself, even though they have different measures, we can create this unit fraction. So the two unit fractions that we will use, since I can reduce this, will be 180 degrees over pi, or pi over 180 degrees. And when we need to convert, we're going to multiply by one of these or the other. Now, if we are going from radians to degrees, we want the radians on the bottom and the degrees on the top to cancel. And if we're going from degrees to radians, we would use pi over 180. So, for example, if we want to convert negative 135 degrees to a radian measure, so I'd say, well, I have negative 135 degrees. Now we can always turn something into a fraction, so technically that's over a little invisible 1. If I want to convert this to radian measure, that means I want to cancel those units. So I need degrees over degrees, which means I'm going to choose this second one. I'm going to say, all right, well, I'm going to multiply by pi over 180 degrees. So you see I have degrees in the top, degrees in the bottom. They cross out, and I'm left with just negative 135 pi over 180. And of course that fraction reduces, and we have negative 3 pi over 4. So what we have is an equivalent radian measure for this given degree measurement. And if we disregard the negative and we go back to our unit circle and we think about 135 degrees, there is 3 pi over 4. So 135 and 3 pi over 4 are the same measure. This works for any measure, even values that aren't on the unit circle. If we think about measuring negative 135 degrees, that takes us over here on the unit circle to 5 pi over 4, or as we just calculated, negative 3 pi over 4. Okay, so all of these are coterminal, meaning they stop on that same angle rotation mark. So in this problem, we're asked to find both a positive, only a positive, but we could find a positive and a negative coterminal angle. In order for us to find that coterminal angle, we're going to add or subtract an entire unit circle rotation. So coterminal, if I add 360, I would come back to the same. Of course, when we're thinking about radians, instead of adding 360, I'm going to add 2 pi because 2 pi is the same as 360. So adding 2 pi, that's the same as adding 8 pi over 4. We have 5 pi over 4. So that's a positive coterminal radian angle. And you see that 5 pi over 4, that's the same spot where we were located. And of course, we could go the other direction. I could subtract negative 2 pi. And thinking about 2 pi in fourths, that's negative 8 pi over 4. So negative 3 minus negative 8 gives me negative 11 pi over 4. So this is a negative coterminal angle. All right. Let's think about just another example here. We'll say convert 92 degrees to radians. So we can convert anything, not even values or not only values that are on the unit circle. If I were to convert 92 degrees, I'm going to think about that 92 degrees like it's over an invisible one. We want to go to radians. We have two unit fractions. I can use 180 degrees over pi or pi over 180. Again, since I want to cancel degrees, I'm going to put that degree value on the bottom and pi on the top. So multiplying this, I've got 92 pi over 180, and that reduces to 23 pi over 45. Vice versa, I could take a radian measure and say we will convert pi over 12 into degrees. So in this case, I'm going to take that pi over 12 value, and when I consider which one of these to multiply it by, I want degrees in the top. I want the degrees to remain. I want those pi's to cancel. So if I multiply by 180 over pi, that leaves me with 180 degrees divided by 12, which leaves me with 15 degrees. All right, so I hope that clears it up for you a little bit better about how to convert between radian and degree measure. You're always going to be multiplying by one or the other of these two unit fractions. All right, so let's go back and talk about radian measure as well as linear speed, because that's going to lead us into actually using our unit circle. So here we're going to think about radian measure and how it relates to linear speed. So radian measures some angle theta, right? So we've got this angle measure right in here. This picture is a little tiny, but there's my theta. All right, so theta is that angle measure. And it's a really tiny little bit in there. So I'm just going to mark it with this red little arc. My notes don't, or my pen doesn't fit as well as my notes do on this screen. So we've got theta. And then we have this distance s. And s, eventually in mathematics, it begins to measure arc length for us. So we're talking about the relationship between this little angle theta and that length along the unit circle. So the radian measure theta of a rotation is the ratio of the distance s traveled by a point at radius r from the center of the rotation. So this radius is right here, and we're talking about this point right at the end. So essentially what we can say is that that angle theta is equal to that arc length divided by the radius. So linear speed we'll refer to as v, like v for velocity, but speed is positive velocity. So v is the distance traveled per unit time. So v is going to be that arc length, this distance divided by time. Angular speed, which we actually use kind of an omega symbol for. So this W or omega mean the same thing, but angular speed is the amount of rotation per unit time. So it's that angle divided by t. So using these formulas, we can develop or derive this formula, and we can say linear speed in terms of angular speed. So v being linear speed, omega representing angular speed. The linear speed v of a point is the distance r from the center of a rotation given by v equals r omega, where omega is the angular speed in radians per unit time. So we have two examples, and we'll use a different formula for each of these examples. The first example, we have a wheel with a 30 centimeter radius rotating at a rate of 3 radians per second. What is the linear speed of a point on its rim in meters per minute? All right, so a couple of things that we need to pay attention to here. We've got centimeters, meters per minute, and 3 radians per second. So we've got lots of different units going on. Since the question wants the answer in meters per minute, I'm going to convert everything into that measurement. So my radius, I have r equals 30 centimeters, and in meters, that would be 0.3 meters. So we also know the rate at which it's rotating. So that's the angular speed, omega. And omega is 3 radians per second. And we need to convert that into radians per minute. So we multiply by a unit fraction here. We know that there are 60 seconds in 1 minute. And I put seconds on the top because I want that to go away. Multiplying that, I get 180 radians per minute. Now again, we don't generally write that word radians. All right, so if we want the linear speed, that would be V equals R omega, so 0.3 meters times 180 radians per minute. And simplifying this, multiplying those two values, I end up with my linear speed V is 54 meters per minute. All right, let's look at one more example. We have an Earth satellite in circular orbit. We know its height, 1,200 kilometers high, makes a complete revolution every 90 minutes. Considering that we know the Earth's radius is approximately 6,400 kilometers, what is the linear speed of the satellite? So you have to think about what the radius is in this problem. So here's my Earth, and the Earth has a center. And we know what the Earth's radius is. That right here is 6,400. Now, the satellite's up in the air, and it goes around. It takes about 90 minutes to make that full circular rotation. We also know the height of this satellite. That is 1,200. So 6,400 plus 1,200, my radius, R, is going to be 7,600 kilometers. And that 7,600 came from summing the 6,400 and the 1,200, these two values. So if we're asked to find the linear speed, we're going to use our equation, V equals R omega. We know the R. What is the omega? Well, scrolling back up, we know that omega is the theta divided by the time per unit time. So in this situation, if I say omega is theta divided by t, well, that means we're going to make 2 pi radians. Remember, these calculations work in radian value, so 2 pi radians divided by 90 minutes. And that's going to give me pi over 45 minutes for omega. And omega is my angular speed. So V is just going to be the product of these two values, 7,600 times pi over 45. And if we simplify that, we're going to get V equals 531. Thinking about the units, that is kilometers per, this was radians over minutes. So we've got kilometers per minute. All right, so that concludes our video. Moving forward, we're going to talk about using the unit circle as well as graphing our basic trig functions, sine, cosine, tangent, also considering their reciprocal functions, secant, cosecant, and cotangent.